Welcome to the Deep Dive, the show where we dig into complex topics and really try to get to the heart of what makes them tick.
Helping you understand the core concepts.
Exactly. Today, we're looking at something absolutely vital, but maybe a bit hidden, the microcirculation. It sounds small, but it's like the real workhorse of the cardiovascular system, isn't it? Where everything important actually happens.
That's a perfect way to put it. It's the true business end. Our mission today is to unpack Chapter 20 of Boron and Boulpaep's Medical Physiology, focusing right on the microcirculation.
Okay.
We want to demystify how your tissues get fed, how waste gets cleared out, and how this whole incredibly complex system stays in balance. We'll turn these dense concepts into something really clear.
Step by step, connecting it to the real world, the clinic.
Precisely. We'll look at the structures, the forces involved, and why understanding this is so fundamental for anyone in medicine or biology.
Fantastic. Let's dive right in then. So when we think cardio, it's often the big pipes, arteries, veins, but the microcirculation, where does that actually start and end? What is it?
Right. So the microcirculation is basically that whole network of the tiniest blood vessels. It starts from the first order arterioles, those are the smallest branches coming off the arteries, goes through the whole capillary network, and then collects into the first order venules, the very beginning of the veins.
And its main job.
Its absolute core function is maintaining the perfect environment for your tissues. It's the place for exchange. We're talking oxygen, CO2, water, nutrients coming in, waste products going out. This is where blood really interacts with the cells.
Okay, so feeding and cleaning primarily. Oh, but you mentioned it does other things too, not just nutrition.
Oh yeah, definitely. Beyond that basic nutritional role, it has some really crucial non-nutritional functions. Think about the kidneys, the capillaries and the glomeruli.
Yeah.
Their job is filtration, forming the glomerular filtrate. Step one in making urine. Very specialized.
I see.
Or in the skin, you have these things called arteriovenous anastomoses. They're like little bypasses that skip the main capillary bed. And they're super important for controlling blood flow to regulate body temperature.
Ah, interesting.
And it doesn't stop there. Microcirculation delivers hormones for signaling, platelets for clotting, and defense. It's really involved in a lot.
Wow, okay. So paint a picture for us. How does the blood actually flow through this tiny network?
Okay, imagine blood coming in from an arteriole, a small muscular vessel. This branches into a really dense web-like network of true capillaries. That's where most of the exchange happens.
Right.
Then the blood flows out of these capillaries and collects into venules, which start merging to form larger veins, heading back to the heart. Now, there are also these little shortcuts called medarterioles.
Shortcuts.
Yeah, they can act as sort of a bypass channel, allowing blood to go more directly from the arteriole to the venule, skipping some of the capillary bed. And both the arterioles and these medarterioles have smooth muscle, giving them control.
And you mentioned precapillary sphincters. They sound like actual gates.
They pretty much are. They're tiny little cuffs of smooth muscle, right where a true capillary branches off an arteriole or sometimes a medarteriole.
Like a valve?
Exactly like a valve. They can clamp down and stop blood flow into that specific capillary, or relax and let it through. What's really fascinating is that unlike a lot of vascular smooth muscle, these sphincters often don't have direct nerve control.
Oh. So how are they controlled?
They respond directly to the local conditions in the tissue around them. Things like oxygen levels, CO2 levels, metabolic byproducts. The tissue itself tells the sphincter whether it needs more blood flow or not. It allows for really fine-tuned local regulation.
That's clever. So looking at the vessels themselves, as we go from arterial down to capillary, how do they change structurally?
Well, the arterioles, the ones feeding the bed, they have a pretty continuous single layer of vascular smooth muscle cells. Gives them good control over resistance.
Okay.
Medarterioles are a bit different, shorter, and their smooth muscle layer is discontinuous, sort of patchy, so maybe less forceful control there.
And the true capillaries, the exchange vessels, what are they like up close?
They're incredibly simple and delicate. Just a single layer of super thin endothelial cells. We're talking like 200, 300 nanometers thick.
Wow.
Yeah, wrapped in a basement membrane and some fine collagen fibers. Sometimes you find cells called pericytes embedded in the basement membrane too, especially in some tissues.
And these endothelial cells, they're not just passive barriers, are they?
Not at all. They're very active. They have these tiny pits on their surface called caveoli involved in grabbing molecules. They also form pinocytotic vesicles, which are like little bubbles that shuttle water and water-soluble stuff across the cell. It's a process called transcytosis.
So transporting things through the cell itself.
Exactly. Sometimes these vesicles can even link up temporarily to form transient channels right through the cell.
And how are the cells connected to each other, the junctions?
Right, between the cells you have interendothelial junctions. These are typically narrow spaces, maybe 10 nanometers wide. But in some places, they form tight junctions, where the cell membranes actually fuse together, sealed by special proteins like claudins and occludin. These really limit what can pass between the cells.
Okay.
And then you have fenestrations. These are actual pores or windows that go through the endothelial cell itself. Little membrane-lined tunnels, about 50–80 nanometers across.
Where would you find those?
You find fenestrated capillaries, mainly in tissues that need really large fluxes of fluid and small solutes. Think the intestines absorbing nutrients, glands secreting hormones, or the kidney filters.
So clearly different levels of leakiness. How do we categorize them?
Yeah, we usually group them into three main types based on how leaky they are. First, continuous capillaries. These are the most common type, found in muscle, skin, connective tissue, the lungs. Their junctions are relatively tight, allowing only small molecules through between the cells.
And the brain.
The blood-brain barrier is a special case of continuous capillary. It has exceptionally tight junctions, almost completely blocking paracellular movement from most solids. Very protected.
Okay, type 2.
Fenestrated capillaries. These are the ones with the pores, the fenestrations going through the cells. As I said, common around epithelia involved in fluid transport, gut, glands, kidneys.
Got it. And the third.
Discontinuous capillaries, often called sinusoids, these are the leakiest, found in the liver, bone marrow, spleen. They have large fenestrations and big gaps between the endothelial cells. Allows even large proteins and sometimes even blood cells to pass through.
So a whole spectrum of structures tailored to the job. And after the capillaries, blood flows into
the venules. They collect the blood. Structurally, they start small, kind of like arterioles, but generally thinner-walled. And they also have some smooth muscle. So they can play a role in regulating flow, and even some exchange can still happen there.
Right. Okay. So that's the structure sorted. Now let's get into the action, the exchange itself. How do gases like oxygen and CO2 get across?
Gases are the easy ones, relatively speaking. Because they're lipid-soluble, they diffuse really easily right across the endothelial cell membranes and through the cell interior. It's called the transcellular route.
Straight through the cell.
Yep, pretty much unimpeded. It's very efficient. There's a classic model by August Crowe, the tissue cylinder model, that helps visualize this.
Tell me about that.
Imagine a single capillary running down the middle of a cylinder of tissue it supplies. Crowe's model helps us understand how oxygen diffuses out from the blood into that tissue cylinder, and how factors like flow rate, tissue consumption, and capillary spacing affect the oxygen levels at different points.
And is the spacing, the capillary density, the same everywhere?
Oh, not at all. It varies hugely. Tissues with really high oxygen demands, like your heart muscle, have an incredibly dense capillary network.
Makes sense.
Whereas tissues with low metabolic rates, like cartilage, have very few capillaries. The lungs are another extraordinarily dense to maximize gas pickup.
How do we actually measure how much oxygen an organ is using?
We look at the whole organ oxygen extraction ratio. You measure the oxygen content in the blood going into the organ arterial and the content in the blood leaving venous. The difference divided by the arterial content gives you the percentage of oxygen extracted.
So if arterial O2 is 20 and venous is 15.
And the difference is 5. So 5 divided by 20 is 0.25 or 25% extraction.
Okay. And what mainly determines that ratio?
Two key things. Capillary blood flow and the tissue's metabolic demand. If you increase blood flow, blood whips through faster, giving less time for oxygen extraction, so the ratio tends to go down.
Right.
But if the tissue starts working harder, as metabolic demand goes up, it pulls out more oxygen, and the extraction ratio increases. It's a direct relationship, really aligns with the Fick principle.
This seems super relevant for something like exercise.
Absolutely perfect example. Think about skeletal muscle. At rest, maybe only about 20% of its capillaries are actually open and being perfused with blood.
Yeah.
The others are kind of shut off by those precapillary sphincters. But start exercising. The muscle needs way more oxygen. So you get vasodilation, the arterioles open up, the precapillary sphincters relax. This massively increases total blood flow, and it recruits all those previously closed capillaries.
So more flow and more open capillaries.
Exactly, which effectively reduces the diffusion distance for oxygen. Each capillary now serves a smaller tissue volume. So even though blood is flowing faster, oxygen delivery becomes much more efficient to meet that high demand. It's a fantastic local adaptation.
Okay, so gases go through the cells. What about small water-soluble things like glucose, amino acids, ions, urea?
For them, the endothelial cell itself is a pretty significant barrier because they're not lipid soluble. They primarily cross via the paracellular route.
Meaning between the cells?
Exactly. They squeeze through those interendothelial clefts, or if present, through fenestrations or gaps.
And Fick's law still applies here.
It does. Fick's law of diffusion tells us the flux, the rate of movement, depends on the concentration difference across the wall, and the permeability coefficient, px. This ficus basically reflects how easily that specific solute gets through that specific barrier. Leakier capillaries have higher px values.
And for a whole organ.
For the whole organ, the total transport depends on the product of that permeability and the total capillary surface area available for exchange, px times s, and also on the blood flow rate, f.
And this permeability, PXS, it must vary a lot between organs.
Hugely. Take a sugar like inulin. Its PXS value is way higher in the heart compared to resting skeletal muscle, partly because the heart has a denser capillary network, meaning more surface area, S.
And the blood-brain barrier again.
The BBB is the extreme case for these solutes. Those super tight junctions mean the paracellular pathway is virtually closed off. So permeability to things like sucrose or inulin is incredibly low, protecting the brain environment. Water, interestingly, still gets across reasonably well, probably transcellularly via aquaporin channels.
So PXS isn't fixed for a given tissue. It can change.
That's a really important point. No, it's not fixed. First, the perfused surface area S can change dramatically based on how many capillaries are open, controlled by those arterioles and sphincters.
Right, like an exercise.
Exactly. And second, the endothelial cells themselves can actively change their permeability, px. During inflammation, for example, chemicals like histamine cause the cells to contract slightly, widening the gaps between them, making the capillaries much leakier.
And even for the solutes that can get through the gaps, does size matter?
Yes, very much. There's what's called the small pore effect. For lipid-insoluble molecules, permeability drops off pretty steeply as the molecule gets bigger. Sodium chloride crosses more easily than urea, which crosses more easily than glucose, and so on.
Like a sieve.
Exactly. It suggests the gaps act like pores, maybe around 3 nanometers radius. The current thinking is that this isn't just empty space, but contains a meshwork of glycoproteins, part of the endothelial glycocalyx, or within the cleft itself, acting as a molecular filter.
And electrical charge, does that play a role too?
It definitely does. The glycocalyx and other structures in the clefts have fixed negative charges. This tends to repel negatively charged molecules, like most plasma proteins, making it harder for them to pass. Conversely, positively charged molecules might pass through a bit more easily. This charge selectivity is super important in places like the kidney glomerulus, helping keep proteins out of the urine.
Okay, one more thing here, solvent drag.
Yeah. Solvent drag is basically solutes getting swept along with the bulk flow of water as it moves across the capillary wall. It's a convective movement. For small solutes, though, diffusion is usually way more important than solvent drag. It's a minor contributor for them.
Got it. Okay, let's move on to the really big molecules, macromolecules like albumin and other plasma proteins. How do they cross?
Right. These large molecules, generally with a radius bigger than 1 nanometer, cross capillaries at a very, very low rate normally. They might use the larger gaps in discontinuous capillaries, like in the liver.
But in continuous capillaries?
In continuous capillaries, the main route is thought to be transcytosis, using those caveolae vesicles we mentioned earlier. It's often called the large pore effect, even though it's a vesicular process, not a fixed pore. It's a multi-step thing. The molecule binds or gets engulfed into a vesicle on the blood side, the vesicle pinches off, shuttles across the thin endothelial cell, and then fuses with the membrane on the tissue side, releasing its cargo.
So an active transport system.
Pretty much, yeah. It's much slower and more selective than diffusion through clefts.
And does size still limit this process? Is there sieving for these large molecules too?
Yes, definitely. The apparent permeability for macromolecules via transcytosis drops off very sharply as the molecular size increases. Bigger molecules cross much less readily than smaller ones. Maybe the glycocalyx hinders access to the vesicles, maybe forming those fused vesicle channels right across the cell is a rare event.
And the blood-brain barrier. Low transcytosis too.
Extremely low. The tight junctions limit paracellular passage, and transcytosis rates are also very suppressed in the BBB, providing that extra layer of protection for the brain against large circulating molecules.
Okay, that covers solutes. Now for the big one, water exchange. Bulk fluid movement. This is Starling forces territory, right?
Exactly. While diffusion handles the massive two-way exchange of water molecules, the net movement of fluid across the capillary, whether fluid filters out or gets absorbed back in, is driven by convection, governed by Starling's hypothesis from way back in 1896.
And it's about a balance of pressures.
Precisely. Two main pairs of forces. First, the transcapillary hydrostatic pressure difference. That's the difference between the blood pressure inside the capillary, PC, and the fluid pressure in the interstitial space outside, PIF.
PC minus PIF, pushing fluid out.
If PC is higher than PIF, yes, it pushes fluid out. The second force is the effective osmotic pressure difference, often called colloid osmotic pressure or oncotic pressure difference.
Okay, what's that?
That's due mainly to proteins dissolved in the plasma versus the interstitial fluid. Plasma proteins like albumin are concentrated inside the capillary and tend to pull water in. That's the capillary colloid osmotic pressure, pi c. Interstitial fluid has some protein too, pulling water out slightly. That's pi if. So the difference pi c minus pi if represents the osmotic pull.
And there's that sigma factor, the reflection coefficient.
Right. Sigma accounts for how leaky the capillary wall is to the solute, causing the osmotic pressure in this case, mainly proteins. For plasma proteins in most capillaries, sigma is close to 1, meaning the wall reflects them. They can't crash easily, so they exert their full osmotic potential.
Whereas for small ions.
For small ions like sodium and chloride, sigma is very close to 0. They cross so freely they don't really exert an osmotic pull across the capillary wall itself.
So putting it all together gives us the Starling equation.
You got it. The net fluid movement, JV, equals the hydraulic conductivity, LP, a measure of water permeability, times the sum of these pressure differences, JV of PC piece.
That whole term in the brackets.
That's the net filtration pressure. If it's positive, fluid filters out of the capillary. If it's negative, fluid gets absorbed in.
Okay, let's unpack those individual forces. Capillary hydrostatic pressure, PC.
PC isn't constant along the capillary. It's highest at the arteriolar end, maybe around 35 millimillar Hg typically, and drops to about 15 millimillar Hg at the venular end as blood flows through the resistance of the capillary.
And what determines its value?
It's influenced by arterial pressure, venous pressure, and the resistances before and after the capillary. Interestingly, PC is often more sensitive to changes in venous pressure than arterial pressure, and it varies a lot by location.
Like the kidney.
Exactly. Kidney glomeruli need high PC, maybe 50 millimillar Hg, to drive filtration. Lung capillaries need very low PC, 515 millimillar Hg, to prevent fluid from flooding the air sacs. It also changes with things like posture, gravity, and vasomotion.
What about the pressure outside interstitial fluid pressure, PIF?
PIF is tricky to measure accurately. In loose tissues like under the skin or in the lungs, it's thought to be slightly negative, maybe negative 2 millimilli Hg, partly because the lymphatics are constantly sucking fluid out.
Negative pressure.
Yeah, slightly below atmospheric. But in enclosed spaces like bone marrow or the brain, or encapsulated organs like the kidney, PIF can be positive, providing some structural support.
And how does it respond if fluid builds up? Does it just keep rising?
Not exactly. The interstitium has interesting compliance properties. Initially, adding a small amount of fluid makes PIF rise quite steeply. It's low compliance. But if fluid continues to build up, the tissue structure can kind of give way and it becomes high compliance. Then large volumes of fluid can accumulate with only small further increases in PIF. That's how you get massive swelling or edema.
Okay, now the osmotic forces. Capillary colloid osmotic pressure, PIC.
Pi c is generated mainly by the plasma proteins, especially albumin, that are trapped inside the capillary. It's typically around 25 millimillar Hg, and it acts to pull water into the capillary. Remember, sigma is near 1 for these proteins.
And interstitial colloid osmotic pressure, pi.
That's due to the small amount of protein that does leak into the interstitial space. It's much lower than pi's, usually estimated from lymph protein concentration, maybe around 3 to 5 millimilli Hg on average, pulling water slightly outwards.
So putting it all together, what's the net result in a typical capillary?
In a standard systemic capillary at the arteriolar end, PC is high, maybe 35 millimilli Hg, pi c is about 25, PF is slightly negative, pi f is low. So the net filtration pressure, PC is positive, maybe plus 10 or plus 12 millimilli Hg. Fluid filters out.
Okay.
As blood flows along, PC drops. By the venular end, PC might be only 15 millimilli Hg. Now the osmotic pressure pulling water in is stronger than the hydrostatic pressure pushing out, PC puff. The net pressure becomes negative, say negative 5 millimilli Hg. So fluid gets absorbed back in.
So filtration at the start, absorption at the end.
That's the classic picture. Net movement out followed by net movement back in. Though there are exceptions. Well, capillaries in the intestinal lining are geared for absorption along their whole length. And kidney glomerular capillaries are designed for filtration along their entire length.
And overall, across the whole body, there's a slight mismatch, right? More filtration than absorption.
Yes. The classic estimates by Landis and Pappenheimer suggested about 20 liters filtered out per day and maybe 16-18 liters reabsorbed. So a net filtration of about 2 to 4 liters per day leaks out into the interstitial space.
And that fluid has to go somewhere, which leads us perfectly to edema.
Exactly. Edema is just that, an excess buildup of salt and water in the interstitial space. And it happens when the balance of startling forces gets disrupted.
How?
Several ways. You could have increased capillary hydrostatic pressure, PC. Standing for hours makes your ankles swell due to gravity increasing PC. Heart failure is a big one. Right-sided failure backs blood up into systemic veins, raising PC and causing edema in the body or ascites in the abdomen. Left-sided failure backs blood into the lungs, raising pulmonary capillary PC and causing pulmonary edema.
What about the protein side?
If you have decreased plasma protein concentration, meaning lower pyre, the osmotic pull into the capillary weakens. This happens in kidney disease where protein is lost in urine, nephrotic syndrome, or severe malnutrition, or even sometimes pregnancy. Less pull inwards means more fluid stays out.
Can the capillary wall itself be the problem?
Absolutely. Increased capillary permeability, meaning LP goes up or sigma for proteins goes down, lets fluid and protein leak out more easily. This is classic in inflammation, caused by histamine and cytokines. Burns, allergic reactions, infections, all can cause leaky capillaries and swelling. Even severe head injury can break down the BVB, leading to cerebral edema.
And finally, the drainage system.
If lymphatic drainage is blocked or insufficient, that 2 to 4 liters of net filtered fluid can't get back to the blood, and it builds up. We see this sometimes after surgery involving lymph node removal, like for cancer treatment.
Before we leave, Starling, you mentioned the model has been revised a bit for continuous capillaries.
Yes, some newer research suggests the classical view might be a bit too simple, especially for continuous capillaries. The revised thinking emphasizes the luminal glycocalyx, that sugary coat on the inside of the endothelial cell, as the primary barrier determining the effective colloid osmotic pressure difference.
So not the whole interstitial space, but right under the glycocalyx.
Kind of. It introduces the idea of a tiny subglycocalyx space between the glycocalyx layer and the cell membrane. The protein concentration, and thus the osmotic pressure in this space, might be different from the bulk interstitial fluid. Fluid movement across the glycocalyx depends on the pressure difference between the capillary lumen and the subglycocalyx space.
And what does that change?
This model seems to better explain why the measured net fluid fluxes are often smaller than the classical model predicted. It also helps explain something called osmotic asymmetry, where filtration might be more favored than absorption under certain conditions. It's a more nuanced view acknowledging the role of that endothelial surface layer.
Fascinating. Okay, so we have this net 2-4 liters of fluid plus leaked proteins leaving the capillaries each day. How does it get back? That must be the lymphatics.
That is exactly the job of the lymphatic system. It's the crucial return route. It starts as these tiny blind-ended vessels called initial lymphatics right in the interstitial space.
How are they structured?
They're made of endothelial cells too, but their edges overlap, forming one-way microvalves. These flaps are tethered to the surrounding connective tissue by anchoring filaments.
So how does fluid get in?
When the interstitial fluid pressure rises slightly, it pushes the tissue outwards, pulling on those anchoring filaments. This opens up the flaps between the endothelial cells, allowing interstitial fluid, now called lymph, once it's inside, to flow into the lymphatic capillary.
And it can't flow back out.
No, because if the pressure inside a lymphatic gets higher, or the tissue compresses, it pushes those overlapping flaps closed. It's a neat one-way valve system.
And where does the lymph go from there?
These initial lymphatics merge into larger collecting lymphatics. These have smooth muscle in their walls and also have internal secondary lymph valves to ensure one-way flow towards the bloodstream.
Smooth muscle, so they can pump.
Yes. The smooth muscle in collecting lymphatics contracts rhythmically, a process called lymphatic vasomotion. This intrinsic pumping action actively propels lymph forward. The rate and force of pumping actually increase as the vessel fills and stretches.
So it's not just passive drainage.
Not entirely. External compression helps a lot too. Muscle contractions during movement, breathing movements, pulsations from nearby arteries all squeeze the collecting lymphatics and push lymph along past those one-way valves.
And how responsive is a lymph flow to changes in interstitial fluid?
It's very sensitive, especially when PIF is in its normal, slightly negative or low positive range. Small increases in PIF cause a big increase in lymph flow. helping to buffer against edema formation. However, if PIF gets really high, like in established edema, the lymphatic pumping mechanism can become overwhelmed or less efficient. The anchoring filaments might get too stretched, the valves might not work as well. So severe edema can actually impair its own drainage, creating a bit of a vicious cycle.
And lymph carries more than just water, right? You mentioned proteins.
Critically important. Proteins that leak out of blood capillaries cannot easily diffuse back in against their concentration gradient. The lymphatic system is the only route for returning these leaked plasmaproteins, maybe 100 to 200 grams per day. Back to the circulation. Without it, plasma protein levels would plummet and interstitial fluid would accumulate rapidly.
Does it carry cells too?
Yes, it carries leukocytes, white blood cells involved in immunity, which can migrate into the initial lymphatics from the interstitium. But normally, no red blood cells or platelets.
It really highlights how interconnected fluid movements are. I heard it described as 3 main convective loops. Can you explain those?
Sure, it's a good way to think about it. Loop 1 is the big one, the cardiovascular loop. That's your entire blood circulation, driven by the heart. Massive flow cardiac output is maybe 5 liters per minute, so over 7,000 liters per day circulate.
Okay, huge scale. Loop 2.
Loop 2 is the transvascular loop. This is the movement of fluid across the capillary walls. As we discussed, maybe 20 liters filter out per day system-wide, and about 16 to 18 liters are reabsorbed back into the capillaries.
And the difference between filtration and absorption
Becomes loop 3, the lymphatic loop. This is the net movement of that 2 to 4 liters per day of fluid, plus the leaked protein from the interstitial space through the lymphatic system, and finally returning back into the bloodstream, usually via the subclavian veins near the heart.
So 3 loops handling the bulk flow. But what about just molecular movement, diffusion? How does that compare?
The scale of diffusional exchange is absolutely staggering, even though there's no net flow. Take water. Something like 80,000 liters of water diffuse out of your capillaries every day, and 80,000 liters diffuse back in. Huge turnover. Zero net movement by diffusion.
Wow. And for solids?
Similar story. Glucose, maybe 20,000 grams diffuse into the interstitium daily, but only about 20 grams move via convection, solid drag. Most of that diffused glucose just diffuses right back out. Proteins, I said 100 to 200 grams per day move across, mainly by convection or transcytosis, and only all of that must be recovered by the lymphatics. It shows diffusion handles massive local exchange, while convection handles the net transport, and the loops handle bulk circulation and drainage.
Incredible scales. Okay, so we have this intricate system. How is blood flow actually regulated at this micro level? How do we control which capillaries get flow and how much?
The main control points are the smooth muscle cells in the walls of the arterioles, the metarterioles, and those precapillary sphincters. Their degree of contraction, or tone, determines the resistance to flow before the capillaries, what we call precapillary resistance.
And that resistance is the key determinant of flow into the capillary bed.
Exactly. If precapillary resistance increases, vessels constrict, flow decreases. If resistance decreases, vessels dilate, flow increases.
How does that smooth muscle actually work? What makes it contract or relax?
It's primarily driven by changes in intracellular calcium levels. And increasing calcium activates a cascade involving calmodulin and myosin light chain kinase, MLCK, which leads to phosphorylation of myosin and ultimately contraction.
And relaxation.
Relaxation typically involves lowering calcium levels or activating myosin light chain phosphatase, MLCP, which reverses the phosphorylation, or inhibiting MLCK. Most vascular smooth muscle gets signals from nerves and hormones, and it can also exhibit spontaneous rhythmic contractions, that vasomotion we mentioned with lymphatics.
So there are system-wide signals, but you mentioned local control is really important too.
Critically important. Local regulatory mechanisms within the tissue itself can often override central neural or hormonal signals to make sure the tissue gets exactly the blood flow it needs at that moment.
What kind of local mechanisms?
2 main types. First is myogenic activity. This is intrinsic to the smooth muscle itself. If you stretch the vessel wall, say by an increase in blood pressure, stretch-sensitive channels open, the cell depolarizes, and it contracts. It resists the stretch.
So pressure goes up, vessel tightens itself.
Yep, helps stabilize flow. The second type is response to local chemical factors in the interstitial fluid.
Like the metabolic signals.
Exactly. The key ones are low oxygen, PO2, high carbon dioxide, PCO2, low pH acidity, increased potassium ions, lactic acid, adenosine from ATP breakdown, all signals of increased metabolic activity. In most systemic tissues, these factors cause vasodilation.
Opening the taps when the tissue is working hard.
Precisely. It creates a beautiful negative feedback loop. Tissue activity goes up, oxygen falls, CO2 rises, vessels dilate, flow increases, oxygen delivery improves, oxygen rises, CO2 falls, vessels constrict back towards baseline. It matches supply to demand locally.
And the endothelial cells lining the vessels, are they just passive bystanders?
Oh, far from it. The endothelium is a major player in regulation. It produces potent vasoactive substances. The most famous vasodilator it makes is nitric oxide, or NO.
The endothelium-derived relaxing factor?
That's the one. Sheer stress from blood flow, plus hormones like acetylcholine or bradykinin, stimulate endothelial cells to produce NO. It diffuses locally to the smooth muscle cells, activates an enzyme called guanylate cyclase, increases cyclic GMP levels, and causes relaxation.
Clinical relevance.
Huge. Drugs like nitroglycerin work by releasing NO, causing vasodilation to relieve angina pain. The endothelium also produces other vasodilators like prostacyclin, PGI2, and possibly something called endothelium-derived hyperpolarizing factor, EDHF.
Does it make constrictors too?
Yes, it does. The most potent are the endothelins, especially endothelin 1, ET1. These are powerful, long-lasting vasoconstrictors, often released in response to hypoxia or injury. They bind to receptors on smooth muscle and cause contraction, usually via increasing calcium. Another one is thromboxane A2, TXA2.
This all leads to a phenomenon called autoregulation, right? What's that about?
Autoregulation is the ability of certain vascular beds, particularly in the brain, heart, and kidneys, to maintain a relatively constant blood flow, despite significant changes in the overall systemic arterial pressure.
So if my blood pressure goes up, flow to my brain doesn't just shoot up proportionally.
Exactly. Within a certain range of pressures, as arterial pressure rises, the resistance vessels in the autoregulated organ actively constrict to increase resistance, keeping flow remarkably stable. If pressure falls, they dilate to decrease resistance and maintain flow.
How does it do that?
It's an active local process involving both that myogenic mechanism, increased pressure causes constriction, and the metabolic mechanisms, changes in flow, affect local metabolite concentrations, which then influence vessel tone.
Why is this autoregulation so important?
It's vital for a few reasons. It protects delicate capillary networks from damaging high pressures. It prevents tissues from being overperfused when pressure is high, which would be wasteful. And crucially, it ensures a stable blood supply, and therefore stable oxygen and nutrient delivery and waste removal to organs that are very sensitive to ischemia, like the brain and heart, even if systemic pressure is fluctuating. It's also key for organs like the kidney that rely on stable flow and pressure for their filtering functions.
Makes sense. One last major topic. Sometimes the body needs to make new blood vessels. Angiogenesis.
Yes, angiogenesis is the formation of new blood vessels from pre-existing ones. While the microvascular network is mostly stable in adults, angiogenesis is essential during certain processes.
Like what?
Wound healing is a big one. Also during inflammation, the growth of tumors relies heavily on it, and it occurs naturally in the female reproductive cycle, like in the uterine lining. It can also be stimulated by chronic conditions like ischemia, physical training, or adapting to high altitude.
How does a new vessel actually grow? What are the steps?
It usually starts at a venule. The basement membrane dissolves locally. Endothelial cells get activated, start dividing, proliferating, and then migrate out into the surrounding tissue, guided by chemical signals. They form cords, which then hollow out to become tubes, connect with other tubes to form loops, and eventually recruit smooth muscle cells to mature.
And what drives this? What are the signals?
It's tightly regulated by a balance of pro-angiogenic and anti-angiogenic factors. The star player on the pro side is vascular endothelial growth factor, or VEGF.
VEGF, heard of that.
Yeah, it's a potent mitogen specifically for endothelial cells, stimulating their growth and migration. It's produced by many cell types, often in response to low oxygen. Fibroblast growth factors, FGFs, especially FGF2, are also important promoters. There are others too, like angiopoietins.
And the inhibitors, things that stop vessel growth.
Right. The balance is key. Judah Foltman pioneered the idea of anti-angiogenesis as a way to fight cancer by starving tumors of their blood supply. There are naturally occurring inhibitors like angiostatin, a fragment of plasminogen, and endostatin, a fragment of collagen OK. These molecules can inhibit endothelial cell proliferation or migration or promote their death.
And clinically, where does angiogenesis matter most?
Several key areas. In coronary artery disease, chronic ischemia can stimulate angiogenesis, leading to the growth of collateral vessels that can bypass blockages, sometimes a lifesaver.
But the downside?
The big downside is cancer. Tumors need angiogenesis to grow beyond a tiny size and to metastasize to spread. So inhibiting VEGF and other angiogenic pathways is a major strategy in cancer therapy.
Any other examples?
Diabetic retinopathy is another critical one. Abnormal, uncontrolled proliferation of blood vessels in the retina, driven by factors related to diabetes, is a leading cause of blindness. So controlling angiogenesis is key there too.
Wow. We've covered an enormous amount, from the basic structure to complex exchange, regulation, and even growth. It really drives home how central the microcirculation is.
It absolutely is. We've seen it's far more than just tiny pipes. It's this dynamic, regulated interface, the true business end, where the cardiovascular system fulfills its ultimate purpose, sustaining every single cell in your body through incredibly precise structures, sophisticated exchange mechanisms, and constant fine-tuning of flow.
And for everyone listening, especially students tackling this material, maybe feeling a bit overwhelmed by the details, remember why this matters. Understanding the microcirculation isn't just abstract physiology. It connects directly to understanding disease processes, interpreting clinical signs, and figuring out how treatments work. Whether it's edema, inflammation, shock, heart failure, or cancer, it all comes back to these fundamental principles.
You've just taken a really deep dive into some core physiological concepts. It might seem complex, but breaking it down step by step, focusing on the logic, you absolutely can master this. Keep asking questions, keep connecting the dots. You're building a foundation that will serve you incredibly well. You've got this.